Okay, so off we go. Where y'all left off last time. Sorry I couldn't be here on Wednesday. Not possible. But I'm optimistic that today will be okay. Well, fingers crossed. We'll see what happens. Picking up where we were. This strategic diagram is something I like to throw in. It's not in the book. But there's some really, really important ideas in here. The problem is what I'm going to try to explain to y'all is actually a representation of material that's way too sophisticated for this course. It's just not realistic. It'd be quite a bit higher level of a course. But you don't need to know all of the formalities and sophistications and that kind of thing to be able to benefit from noticing tremendously convenient patterns, right? And analogies. And I am a big believer in patterns and analogies. I feel like if you understand, one thing, and if there is an analogous theorem, then you can use the understanding of the one theorem to help you understand the other. So that's the big idea here. I want to start setting that up. So, y'all okay? Okay. This diagram that I have here, I put a kind of a small version of it here. I have a bigger, sort of fuller version of it in a document that y'all will find in the course resources section, right? This is what I'm going to actually work off of in class here. But it's just kind of an expanded, sort of fuller version. This is just kind of a more compact version. I guess I'll do a few things here on this version. This sequence right here, we call it a sequence, and the idea is, we have an operator here, gradient, that you give me a function, out comes a vector field. And then here's another operator, right? You give me a vector field, out comes a scalar valued function. That's what curl does. And this is what we call an exact sequence. You don't need to worry about the particulars of that. But the idea of an exact sequence is, there's different ways to say this, but everything has a lifetime of 2. Do y'all remember that story that we talked about back in chapter 3, this whole little metaphor of lifetimes, right? So if you have a function, and if you compute its gradient, that'll give you a vector field. If you take the curl of that, you will get 0, right? But furthermore, if you have a vector field, and you compute the curl, and you get 0, and then if you ask the question, hey, is there some function whose gradient is that original vector field? The answer is yes, there is, because everything has a lifetime of 2, and if it didn't, it would have a lifetime of 1. Right? So this whole business about lifetimes is just a fancy way of saying, or a convenient way of saying that you're talking about an exact sequence. Okay. Here's another observation. If you look at the domains on which we evaluate integrals of these things, and let me do that first. We can do integrals, 2-dimensional integrals of functions, and when we do so over 2-dimensional regions. We can do 1-dimensional integrals of vector fields. What's our domain over which we do 1-dimensional integrals of vector fields? Well, we do such integrals over curves, right? Oriented curves. And then, this isn't really an integral, but in some sense you can always plug points into functions, and there is a sense in which you could, kind of stretch the definition of an integral, and in a certain sense of the word it kind of is, but let's not worry about that. So if you look at boundaries as applied to those domains, you get another kind of exact sequence. Now, there is an asterisk here. I guess that's a tilde, but I'm going to call it an asterisk in the sense that, technically what I'm saying is not quite right? But close enough in the sense that can be fixed, and to whatever extent it's a problem is not something we're going to worry about in this class. In the following sense, if you have a 2-dimensional region and you look at its boundary curve, now I appeal to your geometric intuition. If you have a boundary curve of a 2-dimensional region, the boundary of that curve is nothing. Right? Boundaries don't have boundaries. You just got to kind of think that through and persuade yourself, sure enough. Right? And likewise, now again, asterisk, the math crime coming up. If you have a curve that has no boundary, like a closed curve, that actually is indeed the boundary of a two-dimensional region. Right? Now again, asterisk, okay, and I'm telling a little bit of a fib there. And I don't want to get bogged down in the formalities. But for all practical purposes, that's kind of true also. So neat little facts there. Let's see here. Let's look. Oh, I am going to switch back to the. I said I was going to do it on the big diagram. Let's do this here. So let's talk about the theorems that we've studied in 2 dimensions. We've studied Green's theorem, and here's just a kind of a diagrammatic representation of Green's theorem. If you have a 2-dimensional region and you look at its boundary curve, and if you have a vector field and you compute Green's operator, which again these days I'm calling curl more often. I wrote Green here, but let's call that curl. Right? You compute the function that tells you the curl of that vector field. If you look at your original vector field and over the boundary curve you do a vector line integral like so, right? And if you look at the curl and then over your original region you do a double integral like so, you get the same thing. All right, so let me write that a little bit more compactly, and I kind of recopied and compactified down here. If you take the curl of a vector field and the boundary of a 2-dimensional region, and if you compute on both sides, you get the same thing. So again, that's just kind of a diagrammatic talking through, if you will, of the statement of Green's theorem. Okay, now with that in mind, let's think about what does the fundamental theorem of line integral say. The fundamental theorem of line integral says if you have a function and you look at its gradient, if you have a curve and you look at its endpoints, the A and the B, the starting and the ending point, right? Then if you evaluate the function, the original function, on those endpoints, like so, and on the other hand, if you do a line integral of that gradient on your original curve, like so, then you get the same thing. And it practically leaps off the page how analogous this is. In particular, and just for visual convenience, you take the gradient of your function, you take the boundary of your curve, you compute on both sides, you get the same thing. So it's super analogous. And that should kind of blow your mind a little bit, right? Because these are totally different theorems, right? Green's theorem is about how the fluid is rotating and the resulting circulation and double integral, etc. And then you think about the fundamental theorem of line integrals, and it's about how things change and how the gradient keeps track of that. And there's no two-dimensional anything involved. And yet, these theorems have practically the same structure. So again, it's a real eyebrow raiser. Just so you know, this is not a coincidence, right? This is something that people started to notice very soon, very quickly after these theorems were first discovered. And they started wondering, hey, I wonder if these are related in some way. I mean, is there some sense in which these are, like, is there a generalization of these theorems? Are these all special cases of the same general theorem in some sense? Maybe, perhaps, right? And they eventually figured that out. And in fact, yes, these are both special cases of a single generalized theorem. And so not a coincidence at all. These theorems behave analogously because they're the same theorem. There are special cases of literally the same theorem. So I think that is tremendously cool. Now, what's the upshot for y'all? I think it's just cultural advantages to kind of knowing that there are some amazing truths up there that actually connect the theorems that we're working with, right? That's a cool thing to know. You don't want to be unaware of huge points like that, right? But there's also the advantage of the analogy, right? So, for example, the fact that, curl and what it does, namely it's your integrand over here, right, is analogous in this other theorem to gradient and what it's doing over there. Right? So to whatever extent you feel like you have some geometric intuition for how the gradient works, right? You can think, okay, well, what is curl? Curl, well, it's different. It's geometrically it's one dimension higher. Okay, sure, of course it's different, but it's playing a role that's analogous to the role that this is playing here. Right? And so to whatever extent you feel like you understand the role that gradient plays in the fundamental theorem of line integrals, and maybe why, and maybe how to sort of connect, how to justify why gradient does what it does for the fundamental theorem of line integrals, okay, that's a hint to y'all, right, that Green's theorem is going to have some analogous story. The role that it plays in this theorem and why and how it plays that role in this theorem, totally analogous. Right? So there's some really cool ideas in there and some nice opportunities for helping you kind of make sense of things. And by the way, also, a really convenient tool for remembering. Right? So for whatever it's worth, all these different theorems, Green's theorem, fundamental theorem of line integrals, fundamental theorem of calculus, various three-dimensional versions of these theorems that we're going to be talking about over the next couple weeks. I don't remember the theorems. I remember the pattern, right? All the theorems, they follow this same exact pattern. I just remember what order these operators go in, and I remember the pattern, and that tells me all the theorems. That's a pretty cool memory trick, right? Anyway, something to keep in mind, and I hope you'll find that useful. Let's see here. The last thing I want to do on this before we go on is just give you one other, cool point of view that comes from this diagram. There are certain vector fields that we're going to focus on, that we're going to do a lot with. And these vector fields are special. They're really nice. They have some amazing properties. Okay, so I'm just going to give you all a little heads up. I am starting to feel a little pain So we'll see how much longer this lecture can go. If I have to quit, I'm sorry. I'll see what I can do. So here's the special vector fields. The special vector fields are gradients. Vector fields that are the gradient of something, or you might say vector fields that have an antigradient. Okay. These vector fields can be described in a different way. Another way to describe these vector fields is that Green's operator is 0. These vector fields can be described in a third way. And you may recall from the videos that y'all watched last time that every gradient is path independent. And so the way I like to describe path independence, and there's again, using the diagram as much as possible, any two curves that have the same boundary points will give you the same value for the line integral. Right? Remember, that's what a path independent vector field is. So we have 3 different points of view on how to describe the same vector fields. And again, a little asterisk. I mean, technically, you have to worry about regularity conditions. Not our problem. We're not going to worry about that at all. So 3 different descriptions of the same vector fields. Whatever. Who cares? How does this help us? Let's come down here. This is just a preview, but let's think about the 3-dimensional version of this diagram. And you can see I have a 3-dimensional version down here. Again, this file is, this PDF page here is in the course materials. Course materials. I think I misspoke before. This is in the course materials section. 3-dimensional diagram. We'll talk about that later, but here's the preview. And it's just so cool that this works. This pattern of special vector fields in 2 dimensions that can be thought of in 3 different ways. You know, any vector field that has the green property also has the blue property and also has the orange property and vice versa. Works in 3 dimensions too. And even weirder than that pattern, we're going to find a way to make sense of that 1 dimension over. So we're going to find a way, and you can kind of watch for this to happen as we progress through the material. We're going to find special vector fields who are 3-dimensional curls of other vector fields, which are characterized by their divergence being 0. And which are characterized further by having this amazing property that whenever you have 2 surfaces with the same boundary curve, they will give you the same value of this integral, whatever the heck that is, that we haven't even defined yet. Right? So this pattern is tremendous. Keep on the lookout for these ideas here. We haven't even developed most of these ideas yet, right? But as we go through 3-dimensional vector calculus, starting a little bit today, in fact, keep a lookout for relationships between these things. Keep a lookout for this kind of an integral that we're going to, again, hopefully, maybe, possibly start defining today, and the related ideas. So, again, I love patterns. And I think patterns are an opportunity to help you understand ideas, and it's also a tremendous opportunity to remember ideas. Okay. All righty. Moving along. Let's see here, back to, here. So we're done with all this. Okay, so let's talk about how to find antigradients. This is something that in the recordings that y'all watched, again, thanks for y'all's patience on that. But we talked about what you can do with an antigradient, right? This is one of the big necessary steps in using the fundamental theorem of line integrals. And when I showed you the example, I think it was one, maybe, maybe it was 2 of them. Anyway, those examples that we saw, I just asserted, hey, here's the antigradient, right? And you can check that it works. But I never revealed how I found it in the first place. Right? So here's the process. It's just a computation. It's just a little sort of an observation. It's not a deep idea. This is just how you put the puzzle pieces together. And it goes like this. Suppose we have a vector field that actually is a gradient of something. Let's just say. Right? I mean, what would we be able to conclude if we had a vector field that was a gradient? Well, the coordinates would have to be equal, which gives us these 3 equations. Now let's look at these 3 equations, and let's kind of write these backwards, right? Now you've got to think back to single variable calculus. If the derivative of f is p, then f is an antiderivative of p, right? I mean, this is grammatical backwards, basically the same statement, though. This, though, is about partial derivatives. So this is a partial antiderivative, right? Okay. All right. Now, we can't just say this, Right here, not quite, because anytime you take an antiderivative, remember you also have to say plus c. Why do we say plus c? This is a quick flashback to single variable calculus. We say plus c when we take an antiderivative, because when you take the derivative of that constant, you get 0. Well, here we're talking about a partial derivative with respect to x. So we're not going to add just a constant. We're going to add, wrong color. We're going to add anything whose x partial is 0. Right? Anything that I can sort of throw into here, and when I take its x partial I get 0, is perfectly legitimate to add in for free. Right? So not only constants, but any function that just doesn't have any x's in it. So any function of only y and z. Yep. Okay. Likewise for these others. So this antigradient that we're looking for, right? This is the thing we're trying to decide. Does that exist? And if so, how do I find it? That thing just has to satisfy these three equations. Anything that satisfies these three equations is going to work. So I just compute these antipartials. I remember that I'm allowed to add in partial functions, right? Which you might call partial constants, right? They're constants in the sense that their partials with respect to specific variables have to be 0. Anything that fits all three of these forms, and we're in business. So you just play the corresponding game. You write down what the antipartials are. You think about what those constants might be, and try to win the game. That's as simple as that. So here we go. Here's a vector field. It's got 3 coordinates, PQR. Per the formula on the previous page, we're going to take the x antipartial of the first coordinate, the y antipartial of the second coordinate, and the z antipartial of the third coordinate, right? Straight out of what we talked about on the previous page. That's easy calculus. Y'all can do that. Make sure y'all can do that. And then don't forget to add your partial constants at the end. Right? Okay. All right. So the game begins. Can I find a function that's equal to all three of these things? Now, let's make the obvious misinterpretation. Just to get it all out on the table, we are not asking if there is a function that's equal to all three of these things. That's importantly not the question. The answer to that question would be obviously no, because if there's something that's equal to all three of these things would have to equal to each other. They're clearly not. So that's just, irrelevant. Okay. So the question is there a function that equals to all three of these things? So, here's the thing. If there were, this first expression has an x squared y. This second expression has an x squared y. I need the third expression to have an x squared y, but it doesn't. Oh, wait a minute. Maybe it does. Maybe the point is that this could be x squared y also. Right? So, it is all three of these expressions. I can arrange for all three of these expressions to have x squared y as one of the terms. Likewise, xz. Wait a minute, there's no xz. Oh, again, maybe there is. That could totally, no problem, that could be xz. So I've got the flexibility to call that xz. And then last one. I need a minus yz squared. I've got a minus yz squared. Oh, need a minus yz squared. There isn't one. Oh, wait, maybe there is. Again, that could totally, no problem. That could be minus yz squared. So what we see here is that if we just make these appropriate choices then of these partial constants, right, choose according to what the colors say, then as needed, all three of these expressions are exactly the same. All three of those expressions are indeed green plus blue plus orange, that is our anti-gradient. What do you think? Everybody see how the game's played? A little puzzle, right? So you just put the puzzle pieces together, see if you can make it fit, and if you can, boom, you're in business. Okay. All right. Let's see another example. Let's try to find an anti-gradient for this vector field. And before we start with the process, let's go ahead and realize that we're doomed on this one. We have no chance. There's no way we're possibly going to find an anti-gradient here. How do I know? Well, because I can compute the curl of that vector field. If I compute the curl of that vector field, let me get back over to the diagram, back to 2 dimensions. Hang on. Back up to 2 dimensions. I was given a vector field here. We can compute the curl, and we don't get 0. And remember, everything has a lifetime of 2, right? So we've got a vector field. You compute the curl, you get not 0. Then there is no way that there is some function whose gradient is that vector field, because that would then give you a lifetime of 3. Not allowed, right? Not possible. So we know there is no anti-gradient, right? An anti-gradient would suggest a lifetime of 3. Not going to happen. Okay, so with that in mind, right, so, wrong page. Let's see, here we go. We know we're not going to find one. Let's see how the game plays out when, in fact, there is no anti-gradient to be found. Okay, so I'm going to take the first coordinate and take its x antipartial. I'm going to take the second coordinate, take the y antipartial. Usual process. Let's see here. Don't forget to add in your partial constants. Right, again, I don't need these to be equal. I need only for these to be equal. In other words, I have to allow for the flexibility that these functions can kind of be whatever they need to be, as long as their partials are 0. So the game begins. And what do you think? You win this game? Can you make certain choices of that and this to ensure that that and that are always equal? And I don't think you can. I think you're going to lose that game. Try if you like. I think you can persuade yourself pretty quickly that's a losing game. Everybody see? Any questions? Okay. All right. I am cautiously optimistic that this is going to be okay, because I'm at about a 3 right now, and that I can handle. And it's been like 10 minutes, I think. So usually it on-ramps in about 5 minutes. So I think we're going to be okay. All right. Fingers crossed, knock on wood. Okay, so that finishes Chapter 6 for us. We are moving along now to Chapter 7. Chapter 7 is where we're going to start doing the 3-dimensional version of these theorems. Remember, back to the diagram, just for a quick moment, we talked about all of this 2-dimensional stuff, and I've already shown you on the diagram here that there is a 3-dimensional version of all this stuff. Right? And in fact, some of this we've kind of already done. We've, in fact, already talked about the fundamental theorem of line integrals in 3 dimensions. Okay. And we have already introduced back in Chapter 3 these operators called curl and divergence. I didn't tell you anything particularly justified about any of them. I just made some assertions. Right? And we've seen kind of 2-dimensional versions of these things, but we haven't seen the full 3-dimensional versions of this stuff yet, other than, again, just baseless assertions. So as you can predict from the diagram, we're going to find a theorem. It's going to be called Stokes' curl theorem. that fits in right here. It's going to follow the exact same pattern that we've already seen for Green's theorem and the fundamental theorem of line integrals. And we're going to find a theorem right here called Gauss's divergence theorem. Again, it's going to follow the exact same pattern. And these theorems are going to give us justifications. They're going to help us make sense out of the claims that we made back in chapter 3. I made this assertion that curl is kind of a way of measuring local circulation. I called it circulation density, I think, at the time. And divergence is going to give us some indication of where flux is coming from, and we called divergence flux density at some point in the past. And these theorems are going to help give us some more justification for that. Yeah?
Just wondering, history-wise, how far apart did those theorems come to be?
I'm not entirely clear on my memory of the history. I think the first, I think Green's theorem may have showed up in the early 1800s. And I really don't remember about the divergence theorem. I think Stokes's theorem maybe was mid-1800s. I'm really kind of hazy on this, so I'm sure I'll get fact-checked. But it was a long time ago, for sure, a couple hundred years ago. So while we're on the topic of the history, I'll point out that, again, that these theorems were obviously related from the very beginning. Everyone was, oh my God, look at the pattern. That's crazy, right? But the actual formal, precise unification of those theorems didn't happen until I think it was the mid-1900s. It was about 100 years later, right? Maybe more than 100 years later that it took to actually put that together. And I think I may have already mentioned the following, but I'm going to say it again because I think it's amazing. I know people who know the guy who did that, right? Or who knew. Obviously, he's deceased at this point, right? But I knew people who knew the guy, right? So very recent, modern, very sophisticated stuff that eluded Gauss, for example, right? Gauss was this unbelievable, great mathematical mind, like just preposterously good, and he couldn't figure it out. So very sophisticated stuff. Okay. Let's see here. Back to Chapter 7. So we're going to, just like with Chapter 6, we're going to have to develop some tools. And you may recall we talked about parametric curves. We talked about parametric curves a long time ago. Right? And we've done a few things with parametric curves before Chapter 6, but then Chapter 6 where we really needed parametric curves. That's kind of how we define vector line integrals, was with parameterizations. Right? And scalar line integrals, likewise. You can't do it without parameterizations. So now we're going to define something called parametric surfaces. And the analogy is quite strong. Recall that a parametric curve gives position as a function of one parameter. A parametric surface gives position in terms of two parameters. That's all it is. In fact, we've already seen a parametric surface. We didn't say it in that language exactly, but you all recall we wrote down this construction as a tool for describing, let me get my colors straight. We wrote down this construction as a tool for describing points in a plane, in the sense that if you know a vector parallel to the plane and another vector parallel to the plane, but not parallel to the first one, right? Then any starting point you might have in the plane, in other words, given any point in the plane, you can just go by, some scalar multiple of the first direction vector plus, I made a bad color choice here, but oh well, some scalar multiple of the second direction vector, and wherever you start, you can get to wherever you need to be. Right? And so this construction here, again, the way we saw it previously was this allows you to generate all the points in the plane. I'm going to say it here as it gives me position as a function of two parameters, s and t, namely what scalar multiple of v? Let's see, what scalar multiple of v1? What scalar multiple of v2? Those are your two parameters. And then you can generate any point in the plane. Is that cool? Is everybody happy? Okay, now, you do have to abandon one point of view. If you want to talk about the analogy between parametric surfaces and parametric curves, we did rely pretty heavily on, when we're talking about parametric curves, on the idea that the parameter is time. Right? It's a really nice way to think about, that the parameter is telling you how, as time passes, that's how you get your fingers on the idea of time passing, and then you can think that the parameterization is literally tracing out your curve. You can't really do that here because you can't have, I don't know, it depends on how into science fiction you are, but can you really have two notions of time in the same story? I would watch that movie, right? But I don't think I would get that movie. You know what I mean? It's a pretty confusing idea. I don't think that's a healthy point of view. So you just have to kind of retreat away from this idea that your parameter is time and just think of them as just being parameters. They're inputs that produce outputs. Okay. So I'm going to show you a bunch of tools for how to parameterize stuff. And again, it's a tools in your toolbox kind of situation. Wouldn't it be nice if there were just a single way that you do it? But it's not, right? And how do you know which tool to use? Experience, right? So I'm going to show you the tools, show you some examples, and then you're going to do some homework exercises, and that'll kind of help you build up some experience. And the more you do, the more you'll have a pretty good instinct for which to use in which case. So starting with my favorite one, the graph parameterization. We had a graph parameterization for curves. Okay. And we have a graph parameterization for surfaces. So assuming that you have a graph, and again, this is a graph right here, because we've got one variable written as a function of the other two. This only works for graphs. One of the several reasons why we have to be super clear on the difference between a graph versus a level set or an equation or a picture or there's various different things that very often get conflated. So we've got to be super careful about that. If you have, strictly speaking, a graph, the graph parameterization works off basically the same idea as we saw back in chapter 1, namely, let the input variables, plural now, be your parameters, plural now. In single variable, it was let the single input variable be your parameter. Now there's two input variables. Those are your two parameters. That will give you a parameterization of any graph. So let's see that in action. No big deal. Here's a graph. Right? One variable is a function of the other two. I'm going to follow the rule. I'm going to let my input variables, x and y, I'm going to let those be my parameters, s and t. You can see that right there. X and y are s and t. So, okay, fine. Well, then what is z going to be? Or what do I do with z? Well, it says right here that z is this function of x and y, but wait a minute, x and y are s and t. And so that kind of forces me to pick z to be that. Everybody see the little pattern there? Nothing to it. Very algorithmic. This will parameterize any graph. It's super easy to know when you can do this because, again, the condition is just that it is a graph, that one of the variables is a function of the others. So this is a fantastically convenient and super powerful surface parameterization method because, again, easy to identify when you can use it and easy to implement it. Okay. All right. Another quick example. It doesn't have to be z as a function of x and y. Any variable in terms of the other two. So here you'll notice y is a function of x and z. Now, by the way, I'll also point out, since we're here, it didn't come to me written in that way, right? Sometimes you do have to kind of think to yourself, hey, wait a minute, can I work this around? Can I, is y maybe a function of x and z? And then actually do the algebra to actually make that happen, right? But once you've made that happen, then again, these are your inputs. You let them be your parameters, and then this has got to be what it's got to be. Is everybody happy? By the way, if you look at the original equation here again and ask, okay, well, how did I know to solve specifically for y as a function of x and z? And the answer is I didn't. The very first thing I did, the very first thing I would do when I look at an example like this is ask myself, hey, can I solve for z? Because I don't know, alphabetically, I'm kind of accustomed to that being the one that's the function of the other two, and it's comfortable perhaps. And so I look at the equation and nope, can't do it, can't solve for z. And then you try the others, and you'll fail with x as well. But y works just fine. Okay. Likewise in other coordinate systems. So it doesn't have to be a rectangular variable that you solve for in terms of the other two. It could be a spherical variable, for example. So rho, you see here, is a function of phi and theta. Again, reminder, you don't see the theta, but you don't have to see it. I mean, this is a really simple function in terms of its theta dependence. So if you have one variable as a function of the others, again, plug it in basically is the process. Now, because we do need a parameterization to give us rectangular coordinates specifically, right, you do have to do the conversion formulas first, right? The very first thing you got to write down when you're doing a spherical graph parameterization is start with the conversion formulas. But then, again, just like we did previously, if you have one of the variables solved for as a function of the others, stick it on in there. And there's your parameterization. And notice that as required, we have position as a function of two parameters, phi and theta in this case. All right, this next example, we are skipping. You are not responsible for it. We're just going to totally skip the whole thing. Now, if you're up for a challenge, if you're interested in seeing another kind of a cool technique, this is kind of a surface analog of do y'all remember the one that we did way back when with the bicycle and the reflector on the end of the bicycle tire, and it makes this kind of ziggy pattern as you're riding down the street? You can look back into chapter 2. No, one? I don't remember exactly when that was. Chapter 1, I want to say. Anyway, way back when we were first doing parameterizations of curves, there's one with a bicycle tire. This is kind of a surface analog of that, but it's not worth our time, frankly. It's certainly not in the book. This is a luxury when we have the time, and, well, we don't. So no worries about that. This method, also kind of not in the book, and I think that's a tremendous oversight. This is a really important method. I use this a lot. Again, back in the old college days, And so again, engineers, I think y'all will too. Sometimes the easiest way to create a parameterization is to create a whole new coordinate system. And it's actually a surprisingly easy thing to do. I'm just going to show you an example, just kind of, get the ball rolling on this. If you had a torus, aka this donut here, right, surface of a donut, and you wanted to parameterize that surface of the donut, how might you do such a thing? And let's just think about how would I describe, right, if I wanted to tell you where I am on the surface of a donut, if I had some point, wrong color, if I had some point here and I wanted to tell you where I was on the surface of the donut, I mean, there's different ways you could do it. I guess you could talk about the three-dimensional rectangular coordinates of that point. I think that'd be a terrible way to describe your location on the surface of a donut. Let's think about planet Earth. How do we describe our location on the surface of planet Earth? Do we give three-dimensional X, Y, and Z coordinates? Oh my God, that'd be terrible. Right? What a horrible system for describing where you are on the surface of the Earth. We use longitude and latitude. Right? Couple of angles that between the two of them tell exactly where you are. Right? Much more convenient. So we can do the same thing here, and so the big idea is we do have to set up a sort of a starting point. I'm going to set up as a starting point. Let me zoom in so we can see better. I have to get this thing over here so we can see a little bit better. And so from that starting point, we would need to rotate upward by some angle. I'll call that T. That's kind of a donut version of latitude. Right? And then I would have to rotate by some other angle, S, kind of a donut version of longitude. And boom, there you are. That tells you where you are on the surface of the donut. Does everybody see, just geometrically intuition, everybody see what I'm talking about with the S and the T, and just those angles describe that location as long as we've settled on a starting point that'll from which we will do all these computations. Okay. All right. So once you have set up a coordinate system, then all you got to do is describe location in terms of those coordinates. Now there is some work to be done there. But it's just geometry and trig and a little bit of vector algebra. No big deal. I am going to leave these details for y'all to read through. I'm going to hit the big picture for you. But there are details to be checked. Make sure you follow these details. The trig specifically and the vector addition and all the various geometry. But the big idea is wherever I'm trying to get to, I can write down that vector like this. I can write down that vector like this. That then tells me this point here is the sum of those. And that point, if I were to rotate, by the way, here's how you rotate. Right, now again, make sure you're good with the linear algebra and the trig, right? Make sure you can write down on your own, right? Write down a rotation matrix. Here we're rotating around the z-axis, right, per our setup. You just take this point up here, you rotate per this matrix, and lo and behold, you've got your location, right? That tells you your point X. And you will find that that point X is written in terms of your parameters, your new coordinate system, S and T. Right? And again, details to be checked. Make sure you trig, geometry, vector algebra, linear algebra, matrix operations. Right? You got to make sure you're good with all that stuff. So again, the thing that made this happen, right? How did I get to this formula? I got to it in the broad strokes by setting up a coordinate system convenient for my purposes, right? Whatever seems the most convenient, and then solving as needed for position, rectangular position, as a function of those coordinates. That's a really good system. And am I out of time at this? I'm basically out of time. Yep, out of time. Okay, perfect place to quit. We'll draw the line right here. You all have a good rest of your day. See you later. And don't forget about attendance if you came in after I checked the attendance.